Let's see how we differentiate our log functions then. In our examples yesterday, I did the very simple one of log x, and how I did it was changed the subject to the formula. Basically, you could do that with any function, log of any function, and you will always end up with the derivative over the function itself. So derivative on the function itself. And if that base is not e, so it's not the natural log, then we divide by the natural log of a. Now this is where we now have to be careful, because you remember with exponentials when we differentiated, we multiplied by the natural log of the base. But that's the inverse of logs. And with logs, we divide by the natural log. And again, it all comes from that change of base rule. We get something like this. Derivative on function, that's all we have to remember. Derivative on function, so differentiate it, and we just put that function on the bottom. There it is, 3 on 3x plus 5. Derivative on function, 3x squared on x cubed. But I should simplify that to 3 on x. We've got an alternative way of doing that using our log laws. We could pull the 3 out the front and say, well, that's 3 times I'll differentiate log x, which is of course 1 on x, and I get the same answer. Would I bother with something as simple as that? Probably not. I'd probably just do the 3x squared on x cubed and cancel down. But there are some where it might be smarter to use our log laws. The log of log x. So the function we are logging is indeed log x. So it's the derivative of that over that function. The derivative of log x is 1 on x. It goes on that function. Log x, well, we don't like fractions on fractions, so let's tidy it up. We'll push that denominator down. 1 on x log x would be the derivative for that one. Derivative on function. You know, it probably would have been better to write a function like this with another nesting of grouping symbols there, because that could be a little bit ambiguous. Is it the log of x plus 3 and then that whole thing times x plus 2, or is it the log of x plus 3, x plus 2? So actually it probably would be better to nest that into one. What you tend to see is if you are going to multiply a log by some algebra, you tend to put that factor out the front so there is no confusion. So if I see that, I am assuming it is the log of all of that. Okay, derivative on the function. Derivative, well, I'm going to have to use a product rule for that one. So write down the first, diff the second, plus write down the second, diff the first. Tidy that up, and we have it. But again, maybe for something like this, our log laws would be more useful. So before I do the differentiating, let's break that up and make it the log of x plus 3 plus the log of x plus 2. I now actually have 2 very easy things to differentiate there. And the first one's 1 on x plus 3 and the second one 1 on x plus 2. And I guess it all depends what I'm doing with the derivative, because that will find what I need. So that is an answer. But of course, if I'm finding stationary points or something like that, all right, algebraic fractions, pull it together, and yeah, we get the same thing. Quotient rule 1. Okay, wow. Derivative on function. Looks horrible. But there we are. Square the bottom, write down the bottom, diff the top, minus write down the top, diff the bottom. The top there, that fraction minus 3 on x plus 2 squared. Invert and multiply. We've got x plus 2's cancelling. That one, maybe it is a good idea to use our log laws. We can split that into 2 nice easy derivatives to find. 1 on x plus 5 minus 1 on x plus 2. Bit of algebraic fraction work. Which one? Yeah, I probably tend to think the second one's easier as far as potential mistakes. You know what I mean? When you start getting fractions on fractions. But either way, I mean, it works. Okay, the base is not e. Okay, well, that's all right. We know how to handle that. We'll just do it the same way, but also divide by the natural log of the base. So log of 10. Oh, 6's will cancel. So we get 1 on x log 10. You could have done that, but I say, you could use change of base. So that's why our formula has divide by the natural log. Because if I'd chosen to do it this way instead, and said, all right, well look, I'll change the base of this because I know how to differentiate logs with a natural base, so I'll make it a log of a natural base. It becomes log of 6x over the log of the old base, hence explaining why that old base appears on the bottom. Okay, so it's just a lot quicker to go, oh yeah, I know I'm going to end up just simply dividing by the log of that base. Okay, there's the differentiating of our logs.